This is the world's most dangerous metal, and somehow, it still starts as ordinary-looking rock pulled straight out of the ground. But here's what most people don't know. Getting from raw ore to usable uranium is one of the most heavily controlled, heavily guarded industrial processes on the entire planet. Arms security. Radiation monitoring. Steps most factories never need. So how do they actually do it? Safely? At scale? Every single day? That's exactly what you're about to see. Uranium powers nuclear reactors that supply electricity to entire countries. It's also one of the most tightly regulated materials in the world, tracked, secured, and monitored at every single stage. But almost nobody outside the industry actually knows how it gets from the ground into something usable. What you're about to see is that journey: mining, milling, and processing, the general path this raw material takes before it ever becomes nuclear fuel. Coming up, we're going inside the world of uranium production. But there's one specific safety measure used throughout this entire process that most people have never even heard of, something that exists in almost no other industry on Earth. We'll get there. Let's start from the beginning. Here's something that surprises most people right away. Uranium isn't rare in the way you'd think. It's not some exotic substance hidden in one corner of the planet. It's actually more common in the Earth's crust than gold or silver, scattered in trace amounts almost everywhere you look. The challenge isn't finding it. The challenge is everything that happens after you find it. And that challenge starts the moment a mining company decides where to dig. Uranium deposits exist in specific geological formations, and locating them requires extensive surveying. Geologists studying rock formations, taking samples, and using specialized equipment that can detect radioactive signatures underground. Aircraft equipped with radiation detectors sometimes fly low over promising regions, scanning for the faint signals that suggest a deposit might be hiding below the surface. This isn't a quick process. It can take years of exploration, drilling test holes, analyzing samples, mapping underground formations, before a company even confirms there's enough uranium in one location to justify building a mining operation. Many promising sites get abandoned entirely once the data comes back. The ones that move forward represent a tiny fraction of all the ground that ever gets surveyed. Once a viable deposit is confirmed, mining begins, and there are two primary methods used, depending on how deep and how concentrated the deposit is. The first is conventional mining, either open pit or underground, where workers physically extract uranium-bearing rock, just like mining for any other mineral. Heavy equipment digs into the earth, and the ore, rock containing uranium in low concentrations, gets loaded and transported to a processing facility. Open pit operations look almost exactly like any other large-scale mining site from the outside. Massive terraced excavations, heavy haul trucks, towering equipment. The radioactive element hidden inside isn't visible at all. The second method is something most people have never heard of: in situ recovery. Instead of digging up rock at all, a specially formulated liquid solution gets pumped down into the uranium deposit through a network of wells. That solution dissolves the uranium directly underground, and then it gets pumped back up to the surface, carrying the uranium with it, dissolved in liquid form. No massive pit, no underground tunnels, just wells, pipes, and chemistry doing the heavy lifting almost invisibly from the surface. Both methods exist because uranium deposits vary so much. Different depths, different concentrations, different rock types, different surrounding geology. The mining method has to match what's actually underground, and getting that match wrong means wasted time, wasted resources, or worse, an operation that simply doesn't work. Here's where the real challenge becomes obvious. Raw uranium ore, whether it's dug up or dissolved and pumped to the surface, contains only a tiny fraction of actual uranium. We're talking fractions of a percent mixed in with massive amounts of ordinary rock, sand, and other minerals. You cannot use this material as is for anything. It has to be concentrated, separated, and purified before it becomes useful for any purpose at all. And here's the catch. You're not just separating uranium from rock. You're handling a radioactive material at scale, continuously, day after day. Which means every single step downstream has to account for two things simultaneously: extracting uranium efficiently and protecting every single worker who comes near it. Neither one can come at the expense of the other. That's the system we're about to walk through. For conventionally mined ore, the first step at the processing facility, called a mill, is crushing. Massive industrial crushers break the raw rock down into smaller and smaller pieces, eventually grinding it into a fine, sand-like consistency. This step exists for one reason: surface area. The finer the material, the more effectively chemicals can access and extract the uranium trapped inside it during the next stage. Crush it too coarsely, and a significant amount of uranium stays locked inside rock particles, never extracted, wasted, meaning the company spent money mining material it never even managed to use. Throughout this entire crushing and grinding process, dust control is critical. Radioactive dust is exactly the kind of hazard this industry is built to prevent. Enclosed systems, ventilation, and continuous air monitoring run throughout the facility, ensuring that nothing, not a single particle, escapes into an uncontrolled space. Workers in these areas wear protective equipment, and the machinery itself is sealed wherever physically possible to minimize any airborne exposure. Once the ore is ground down, it moves into leaching tanks, and this is where the actual separation begins. A chemical solution, usually involving sulfuric acid or an alkaline compound depending on the ore type, gets mixed with the crushed material. This solution dissolves the uranium out of the rock, while leaving most of the other minerals behind as solid waste. It's essentially a controlled chemical extraction, pulling out exactly what's needed, leaving behind what isn't. The leaching process takes time. The slurry, that mixture of ground rock and chemical solution, gets agitated continuously in large tanks for hours, sometimes longer, allowing the chemistry to fully extract the dissolved uranium before moving to the next stage. Temperature and chemical concentration are both monitored throughout because rushing this stage means leaving uranium behind, unextracted, in the waste. This is also where in-situ recovery rejoins the same pathway. Remember that liquid solution pumped up from underground wells? It already contains dissolved uranium at this point, meaning it skips the crushing and grinding steps entirely and goes straight into a very similar separation process from here. After leaching, what you have is a liquid solution containing dissolved uranium mixed in with leftover solid waste material called tailings. The solids get separated out, filtered or settled away, leaving a clear uranium-bearing liquid behind. The tailings themselves require careful, long-term management since they still contain trace radioactive material even after the uranium has been removed. That clear liquid then moves through a separation process, typically using ion exchange or solvent extraction methods, which pulls the dissolved uranium out of the liquid and concentrates it further. Think of it as refining a refinement, taking something already concentrated and concentrating it even more, stage by stage, removing impurities along the way. Once sufficiently concentrated, the uranium gets precipitated out of solution, meaning it's chemically converted from a dissolved state into a solid form. This solid gets dried and packaged into a coarse yellow powder known throughout the industry by its nickname, Yellowcake. Yellowcake isn't pure uranium, and it's definitely not fuel-ready. It's roughly 70 to 90% uranium oxide, packaged into sealed drums for transport to specialized facilities elsewhere. Facilities equipped to handle the further conversion and processing required before uranium can ever become usable nuclear fuel. But even at this stage, Yellowcake, the security around this material is intense. Sealed, tracked, transported under strict regulatory oversight, with documentation following every single drum from the moment it's packaged to the moment it arrives at its destination. Nothing about this material moves casually. Nothing goes unaccounted for. Every drum is weighed, recorded, and verified against shipping manifests at multiple points along its journey. And here we arrive at the piece we promised in the introduction, the safety measure that exists in almost no other industry on Earth. Every single worker at a uranium facility wears radiation dosimeters, devices that continuously track their personal radiation exposure all day, every day. These readings get logged, monitored, and reviewed constantly, ensuring that no worker ever approaches exposure limits considered unsafe over time. If a reading ever trends upward unexpectedly, that worker's tasks and location get reviewed immediately. Beyond personal monitoring, the facilities themselves are wrapped in layers of detection systems, air monitors, surface contamination checks, water testing around the site perimeter. Ventilation systems are engineered specifically to control radioactive dust and gas, pulling contaminated air through filtration before it's ever released into the surrounding environment. And security is just as serious as the safety protocols. Armed guards, restricted access zones, surveillance systems, and strict material tracking exist specifically because uranium, even in its raw, unprocessed form, is treated as a national security concern, not just an industrial material. Background checks, controlled access points, and constant monitoring are simply part of daily operations here, in a way that would feel completely foreign at almost any other type of factory. This is what makes uranium production fundamentally different from every other factory process we've ever covered. It's not just about efficiency or quality control. It's about protecting people, protecting the environment, and protecting the material itself, simultaneously, continuously, without exception. And once you understand everything that has to happen just to get raw rock to this point, Yellowcake, ready for transport, you start to understand exactly why this industry operates the way it does. Here's what's worth sitting with after everything you just saw. Uranium starts as ordinary rock, scattered through the Earth's crust, more common than gold, completely unremarkable to look at. And yet, by the time it leaves that mill as yellowcake, it's already being treated like one of the most consequential materials on the planet. Tracked, guarded, monitored down to the individual worker, down to the individual drum. That's the real story here. Not just the chemistry, not just the crushing and leaching and separating. It's the fact that an entire industry was built, from the ground up, around one principle. Power this significant demands precision, this exact. There's no close enough when the material itself carries that much weight. And that's exactly why the world's most dangerous metal earned its name. Not because it's mishandled, but because of everything required to make sure it never is. If this kind of high-stakes industrial process is what you're here for, hit that like button, subscribe, and stick around. Because what's coming next on this channel is built for exactly the kind of person who watched this all the way through. Drop a comment below. Tell us which factory or material you want us to go inside next. Your suggestion might just become our next video. See you inside the next one.